Alright, so here we're going to show how we can derive the relation between the kinetic energy and pressure and volume and temperature and see how all these things are related from the kinetic theory of gases. Now just beware that this isn't a very rigorous derivation, but it's appropriate more for a general chemistry kind of thing. If you're dealing with a more advanced class, basically you just need a whole bunch of calculus to actually prove this rigorously, but for our purposes it actually works out pretty good. Alright, so first we're going to just imagine a system where we have one particle moving in a box. Alright, so here's my box, has sides L, so it's a nice little cube. And inside this box I have one little particle, which is moving this way, that has a mass for this particle, and it has a certain velocity. So that's our system, basically one atom, one molecule moving around in a box, and we just want to figure out how we can calculate the pressure from this. So first up, a couple of definitions here. So pressure is equal to force over area. All right. Now force, and this is from Newton's second law, is equal to mass times acceleration. Now acceleration is a change in velocity with time. So we can rewrite this as m delta v over delta t. So what we're going to assume is that this particle here, when it's a completely elastic collision, so when the particle hits the wall and will bounce back, so it's still obviously just going to have the same mass, but it's now going to have the negative velocity. So that means that my change in velocity here is going to be equal to v minus the negative v, which is just going to be 2v. And then my change in time, how long this actually takes it for this to actually occur, is going to be the length divided by the velocity. Okay, so that's just going to be my time, because it's basically the time between collisions. It bounces here, then it has to get back to the other side, back to the other side. So it's going to be the length divided by the velocity. Also here, the area, I should mention this, the area is just going to be L squared. But now if you think about it, this is a cube, right? So I have a top, a bottom, a front, a back, and a left side and a right side. So that's going to be 1, 2, 3, 4, 5, 6. So I have 6 sides here. So my area of my cube is 6L squared. Now we can take this information we have and plug that into there. So this is going to be my force, which is just going to be my m delta v over delta t, over my area, which we just said was 6L squared. So let's plug in my delta V and my delta T there. So that's going to be M times 2V, so that's the 2V there, divided by my delta T, so that's going to be L over V, and then divide that by my 6L squared. And we can simplify this. This L combines with this L squared, so it's going to give me L cubed, and then 1 over v is going to give me v squared. And then the 2 over 6 is just 1/3. So this is going to simplify to mv squared over 3l cubed. Now mv squared over, now l cubed, if we think about this, l cubed, that's what? That's going to be our volume. And I just wrote the volume with this weird little v just so we don't confuse it with the v, which is my velocity. So just so we don't confuse those things. So I can write here that my pressure is equal to mv squared over 3 times the volume. This right there is volume, and this one up here is velocity. Now that means we can obviously just rewrite this as the pressure times the volume is equal to 1/3 mv squared. Now if we remember from before, we mentioned the kinetic energy is equal to 1/2 mv squared. So since the kinetic energy here is equal to 1/2 mv squared, and what we're going to do is define something which is proportional to the kinetic energy of the gas. We're going to say that's going to be the temperature. So we're going to say that the temperature is proportional to the kinetic energy of the gas. And we also know from the ideal gas law that PV here is equal to nRT. So what we're going to do is figure out, well, from this relation, how can we relate this to the kinetic energy? Well, look right here. This is 1/2 mv squared. This is 1/3 mv squared. So therefore, my kinetic energy is going to be 3/2 times the 1/3 mv squared. So 3 halves times 1/3, my 3's cancel, I get 1/2 mv squared, so that's exactly the same. But now that's going to be equal to 3 halves times the pressure times the volume, or we could write that as 3 halves nRT. And this is how we get the relation here that the kinetic energy of the gas is equal to 3 halves nRT. Alright, now like I said, this isn't a rigorous definition. To actually do this would involve integration and everything. But, it does give us, approximately, the correct answer here with a little less fuss.